The test answers on our combustion, stoichiometry, and limiting reagent test. The first question asks, how many moles of oxygen are needed to burn 1.25 moles of octane? So we start off with the moles of octane. We're given the balanced equation, and in the balanced equation, the stoichiometry is 25 to 2. So we multiply it in such a way that moles of octane is cancelled, and we're going to multiply a number by 12.5. 25 over 2 is the same as 12.5. So we end up with 15.625 moles of oxygen. Obviously, we can't report it to that level of accuracy because the question only has 3 significant figures in the data that it supplies. So our answer can only be to 3 significant figures, 15.6 moles of oxygen. Part B, they say, how many grams of oxygen are needed to burn 10 grams of octane? So the first step is to find out how many moles of octane we have. We have 10 grams divided by the molar mass of octane, which is composed of carbon and hydrogen. 8 carbon atoms, 18 hydrogen atoms. So it's 10 over 114. Gives you that many moles of octane multiplied by the stoichiometry of the reaction. 25 moles of oxygen is burned, is consumed for every 2 moles of octane that is burned. This is how many moles of oxygen that turns into. So it's this number times 12.5 gives you this number in moles of oxygen. And then we're converting moles of oxygen into grams of oxygen by multiplying by the molar mass of oxygen. So we get 35.015. We're only allowed 3 significant figures, so we report 35.0. The red arrows signify what I was looking for. So every red arrow will get you a mark in the question. So even if you didn't get the answer, even if you started writing something, I would, if I saw any semblance of understanding, I gave you marks for that. The third question asks, octane has a density of 0.692 grams per milliliter at 20 degrees Celsius. How many grams of oxygen are required to burn 4.25 liters of octane? Use the density formula to calculate the mass of octane. So we know that density is equal to mass over volume. If you rearrange the formula, I gave you a mark for that because you're solving for m. So if you transpose the v so that it's next to the density symbol, then to solve for m, then you got a point for that. Then if you plugged in the numbers correctly, you got 2 points, 1 for each number, and then you got a point for the answer. 2,941 grams of octane, but you're not finished. Some people even stopped right here, and they thought that was the answer. That's not the answer. The answer is, that's halfway to the answer. You take the number of grams of octane divided by the molar mass of octane, which you already calculated over here, so you can simply recycle the number here, putting it there. You have 25 moles of octane times the stoichiometry of the reaction, 25 moles of oxygen per every 2 moles of octane used, gives you 321 moles of oxygen needed to support that combustion reaction. You then multiply by the mass of oxygen to give you the molar mass of oxygen to give you the mass of oxygen consumed. You can't report it to that level of accuracy. You're only now allowed 3 significant figures. So we write 1,030. This 0 doesn't count as a significant figure unless you put a decimal place there. It's a space or 0. If that disturbs you, you could simply write it as an exponent, 1.03 times 10 to the 4 grams of oxygen. That question was out of 11. Second question. It asks, it's the Seltzer question, where they say the fizz produced when an Seltzer tablet is dissolved in water is due to the reaction between sodium bicarbonate and citric acid. So I think I lifted this question from the textbook, Brown and others, chapter 4, or perhaps chapter 3, sorry. In a certain experiment, 1 gram of sodium bicarbonate and 1 gram of citric acid are allowed to react. Which is the limiting reactant? So we have 1 gram of sodium bicarbonate, 1 gram of citric acid, divided by each one of their molar masses, because every question like this has to go to moles. So we're finding out the moles. Here's 1 gram divided by the molar mass of sodium bicarb, 1 gram divided by the molar mass of citric acid. This is how many moles of sodium bicarbonate you add. This is how many moles of citric acid. But before you start comparing the numbers, you have to keep into account the stoichiometry of the reaction. It's a 1 to 3 stoichiometry. 3 moles of sodium bicarbonate are used for every 1 mole of citric acid. So pick one of these 2 numbers. Just pick one. I picked this one. And I multiplied it by the stoichiometry, properly oriented so that citric acid cancels. So I had 5.2 times 10 to the minus 3 moles of citric acid times 3 moles of sodium bicarb being used for every 1 mole of citric acid used, you'll see that the moles of citric acid cancels, and we're left with how many moles of sodium bicarbonate is needed for this reaction. That's how many moles are needed, that's how many moles we have. So because this number is bigger than that number, it tells us that this is the limiting reagent. The sodium bicarbonate is going to finish earlier than the citric acid. Somebody in the last class asked me, sir, what if you start from the other number? I said, fine, let's start from the other number. So I start off with 1.19. I started off with 1.19 times 10 to the minus 2 moles of sodium bicarbonate. Now you'll notice I flipped over the conversion factor. It's the same conversion factor, just inverted, because I'm starting with the other substance. And that allows me to cancel the moles of sodium bicarbonate to find out how many moles of citric acid is needed. That's how many moles of citric acid is needed. Compared to how much we already have, we see that this number is smaller than that number, which means we have extra citric acid. If this is the one that's extra, it means the other one is limited. And that's what I wrote down. Limiting reagent is the sodium bicarbonate. Because we found out the sodium bicarbonate is the limiting reactant, every calculation about yield is going to have to begin from the limiting reagent. So in part B it asks how many grams of carbon dioxide are formed. We start the calculation with the number of moles of sodium bicarbonate times the stoichiometry of carbon dioxide formation versus the amount of sodium bicarbonate used. The stoichiometry is 3 to 3, which is the same as 1 to 1. So you get the same number of moles of CO2 being formed times the molar mass of carbon dioxide, 44.0098. This number comes up often enough that it might be a good idea to just memorize it rather than have to calculate it every single time on an exam. On an exam, if you write this number, I'll assume that you memorized it, because if you have to, how often do people memorize a number like that? So that saves you a step in the exam, and it buys you maybe a minute of time or 45 seconds of time, which can be precious in an exam, especially if you have a lot of questions to answer. At any rate, that gives you the number of grams of carbon dioxide, which we then report to 3 significant figures. 0.524 grams of CO2 is your final answer. I noticed a lot of people were simply not even reporting. They were leaving the original number, or they were reporting to the wrong number of significant figures. Remember, this 0 is a spacer. So these are the numbers that count. If you really want to be sure and not make a mistake when you report significant figures, write all your numbers using scientific notation, because then you won't be writing them with zeros, which tend to cause confusion for a lot of people. The last question is, how many grams of excess reactant remain after the limiting reactant is completely consumed? So that means we have to work with the substance that's in excess. This is how much citric acid we have, 5.2 times 10 to the minus 3. This is how much we need, which we calculated over here. We're using all the numbers that have already been calculated. This number minus that number will tell us how much citric acid is left over in moles. But then we're going to convert from mole quantities to mass quantities. We know the molar mass of the substance because we calculated it up here. So this number times that number tells you how many grams of citric acid is left over, and then again you report it to the correct number of significant figures, which is 3. So 2.376 rounds off to 0.238 grams of citric acid. Any questions? All right.